Hey everybody, it's Todd Francis, and I'm finishing up chapter 18 with thermodynamics. What we finished with prior to spring break, um, we're into the laws of thermodynamics. Our first law of thermodynamics focused on the relationship between heat, work, and the internal energy of a system. We started with, and then we got into entropy, which was this measure of disorder. The second law of thermodynamics, as you see here, the total entropy of a system always increases for a spontaneous process. We can look a little bit at the calculations. This is the one I want to focus on. Again, that change of entropy being greater than heat divided by temperature. This Q divided by T is also known as the heat flow with this. So this gives us a calculation that we can use if we want to calculate the spontaneity of a solution. The next section, I'm not going to talk too much of it. You can read through it, but it does go into the idea that entropy and disorder are hand in hand. And it does give you some examples, whether it be in a coffee cup, the movement of a gas in a container, or even ice melting. We're always looking for that change in disorder for this, and we're always looking for the increase in this disorder. And the relationship is with energy. The more energy is dispersed, the more disorder we have. For a phase transition, and again, one of the things you got to remember with a phase transition is the temperature remains constant. So you can see in a phase transition and equilibrium, now instead of the inequality, the two are equal. With the phase transitions, you may remember heat of vaporization, heat of fusion, and again, that's where those numbers come into play. And we can using those heat of vaporizations or heat of fusion, we can calculate the entropy for a system during a phase change, and that's what you're seeing in this calculation. For a spontaneous process, this equation here is what will hold true. The change in entropy minus change in enthalpy minus the temperature times the change in entropy is going to be less than zero. The key to this equation is twofold. One, the temperature that we're working with is measured in Kelvin. And then two, enthalpy, the delta H, is measured in kilojoules per mole. Entropy is measured in joules per mole Kelvin. Okay, so there will be a conversion of the units from joules to kilojoules in the calculations. The third law of thermodynamics now focuses on what happens when we reach 0 degrees Kelvin. I've mentioned this temperature before. We say, hey, at this temperature, all molecular motion will cease. Well, no molecular motion, no disorder, and you can see the relationship entropy being 0. And with that as a basis, we can calculate what they call a standard entropy. And again, the standard entropy, much like the standard enthalpy, are at set conditions. In this case, 1 atmosphere. If we're working with a solution, it's a 1 molar solution. And you can see in this graph, you can see the increase in entropy. And where the curves flatten out, that's our phase transitions. This is table 18.1. This has a value of, these have values of entropy. You can also go to Appendix C, which is in the back of your textbook. Again, one thing to note here, note the physical states for the substances and the entropies of those. So bromine, both as a gas and a liquid, they have two different entropy values that you can play in. Sometimes we don't have to use numbers. We can look at how what's happening in a reaction. Are we forming more products? A decomposition reaction. Count up the number of gases, moles of gas, if there's an increase in the moles of gas, or a transition to a gas. That's an increase in disorder, and we see that. So we can look at this example here, and we don't have to plug in numbers, but what we can see, again, it's a decomposition reaction. The glucose breaking down into alcohol and carbon dioxide. And because it's that decomposition reaction, we're going to have a value of, delta H, the entropy going to be increasing. We can plug in the numbers. And again, as you look at this equation, products minus reactants. It's always that when it comes to changes. And in fact, you can see that in this example, the reaction of ammonia, carbon dioxide to form urea and water. They give us our values of entropies, and it's just a matter of plugging in the numbers. Again, products, reactants, make sure you note that in there. And again, note the units also. Again, for entropy, it's joules per Kelvin. Free energy is an interesting property developed by Gibbs, but now this is, by definition, they define it as our relationship for the spontaneity of a reaction. So in essence, this delta H minus T delta S, hey, if it was less than 0, we had a spontaneous reaction. If it's equal to delta, and now, hey, delta G, it's going to be that spontaneity also. We can have the standard energy changes. So again, those same conditions, 25 degrees Celsius, 1 atmosphere of pressure. If we're working with solution, 1 molar solution. And note how the numbers are plugged in here. Again, we've got our equation, our delta H values, delta S values. These are coming from whether it be table 18.1, table 6.1, or actually, again, in the appendix C. And again, products minus reactants. Again, note the units here. Delta H is in kilojoules, delta S, joules per degree Kelvin. So there is going to be a conversion for the joules. And we plug that into the equation. Note what they're doing for delta S. Our temperature, 25 degrees Celsius, the 298 degrees Kelvin. And just do the math. Pay attention to your signs here. It's easy to lose those. We can also use standard energy value, free energy values. And this is table 18.2. Also in Appendix C, you have the same table with more substances. Again, pay attention to chemical states. That's going to be important. Products minus reactants. You'll see that. And again, hey, we can just plug in the numbers with this equation. That value of delta G, okay, hey, there's our spontaneity. There is a relationship between work that we talked about at the beginning of this chapter and delta G, and you can see, hey, there's that equivalence to this. The last part of this chapter looks at the relationship to the equilibrium constant, our value of K, value of K sub C. And this is an equation that I want you to note. This delta G is equal to negative RT natural log of K. Again, temperature is going to be in Kelvin. The value for R is going to be different. The value of R that we're going to see in this equation now is this 8.31 joules. It's 8.31 joules per gram, joules per Kelvin mole. Okay. You've got a natural log, so we need to take the anti-natural log, which is that E value. And again, look at your calculator. You can see that second function there. The biggest thing with this equation is we do have that different value for R in this. It is the gas constant, but it's just a different value for the units. The other aspect here, remember delta G, pay attention to the units. You can see the relationship with temperature also, and spontaneity and non-spontaneous conditions for this in our equation. Okay, so that wraps up chapter 18. If you have any questions, please feel free to contact me. Take care.